Welcome back to the Deep Dive, the place where we take the fire hose of information you need and distill it down to pure knowledge gold. Today, we're diving deep into something truly foundational for modern data architecture.
We really are.
We're talking about Google Cloud Storage, or GCS. It's this engine that powers just massive applications all over the globe. But, the thinking behind it, the actual architectural philosophy is, well, it's often misunderstood.
That's absolutely right. I think when most people think about storing data, whether they're just an end user or even an architect designing a huge application, they immediately default to what they know.
Traditional file server.
Exactly. A hard drive with folders nested inside folders. And that mental model, it's familiar, but it will absolutely lead you astray in the cloud. GCS operates on, well, a completely different set of rules.
So it's not just a bigger hard drive in the sky.
Not at all. It's critical infrastructure. And if you don't understand the core concepts, we're talking about buckets and objects, you're going to hit performance bottlenecks or, even worse, make some very, very expensive design mistakes down the line.
Okay, so let's unpack that. Our mission for this deep dive is pretty simple. We are going to extract the core actionable insights about GCS. We want to know what it is, how it's organized, and I think most importantly, why its design choices, like this concept of immutability and the great myth of the folder, are so fundamentally different from everything you've learned about file systems.
Right.
This is really your essential shortcut to being genuinely well-informed about enterprise-grade cloud storage.
So to set the stage, GCS is an enterprise-grade RESTful object storage service.
And that RESTful part is pretty key, right? It means you're interacting with it over standard HTTP calls.
Precisely. You're treating your data just like web resources. And it's all built on, the massive Google Cloud Platform infrastructure.
Which means it inherits all that power. The almost limitless performance, the scalability, the advanced security that Google is known for.
All of it. It's designed from the ground up to store just vast amounts of unstructured data. Think, everything from massive video files to tiny little sensor readings from IoT devices at any scale.
And structurally, it really just boils down to two things.
Two core units. Yep.
You have the container, which GCS calls the bucket, and then you have the actual data itself, the payload, which is the object.
That's it.
So I think we need to tackle the container first, because that seems to be where all the crucial high-level management and the big strategic decisions are made. It's like the governance layer.
It absolutely is. Everything starts with the bucket.
So let's start with the bucket. When I hear that term, my brain, instinctively pictures a directory or a folder. Why is that mental image of just a simple folder so completely inadequate for what a bucket actually is?
Because a folder is really just a passive structure for holding files. A bucket is. It's a critical management unit. It certainly serves as the basic container for all your data in GCS. Everything you store absolutely must reside in one, but its function goes so far beyond just simple containment.
A management unit for what specifically? What are these high-stakes decisions that are tied directly to the bucket?
Okay, so there are three fundamentally important areas. They control your entire deployment, and they are defined entirely at the bucket level. Everything inside just inherits these properties.
Okay.
First, it dictates data residency. So when you create a bucket, you are making a legal and architectural commitment as to where that data physically lives.
You mean which country, which continent?
Exactly, which region or combination of regions globally. And this choice, it impacts your compliance, any political constraints, and of course, network performance. And here's the kicker. You cannot change it later without creating a whole new bucket and migrating all the data.
Wow. Okay. So that's a day one permanent decision. What's the second area?
Second, it is the primary control point for billing. The entire cost structure, the storage class, the location redundancy, even policies for data retention, all of that is tied directly to the bucket configuration. That in turn determines the rate you're billed for both storage and for operations like reads and writes.
And the third?
And third, it's the highest level of access control. Everything inside a bucket inherits the access rules you set on the container itself. It's the fundamental boundary for your data governance. It defines which users, which services, or even which other projects can read, write, or delete the content within.
So if you manage the bucket correct,
You manage everything inside it.
that makes the bucket a major architectural decision right from the start. But here's where it gets really, really interesting, and this is a point that often trips up users,
Yeah.
especially if they're coming from other cloud environments where naming is, usually scoped to an account or a project.
Ah, the global namespace challenge.
Right. You said the bucket name isn't just unique to my project, but globally unique.
This is critical, and it's unique to how GCS implements it. Bucket names are unique across the entire Google Cloud ecosystem. If anyone, anywhere in the world, in any Google Cloud project has claimed a bucket name, let's say Data Lake Finance 2024, that name is instantly unavailable to you, permanently, until that other bucket is deleted.
Whoa. The strategic implications of that they're huge. It means an organization, especially one with a strong brand, has to be incredibly strategic and, frankly, fast about securing their namespace.
It's like registering a domain name.
Exactly. It turns bucket naming into an organizational asset.
It does. You are literally competing with every other user on the planet for that perfect intuitive name. This forces you to have a robust prefix-based naming strategy right from the start. You can't just hope to get common terms like raw data or backup.
You'd have to use your company name as a prefix, maybe a region code.
Something like that. You have to integrate an organizational identifier, maybe a region, and then the descriptive purpose. Because if you wait, someone else will claim that generic, desirable name. This is so much more restrictive than naming, say, a virtual machine or a database, which is usually private to your own project.
So speaking of deleting buckets, if a company claims a name, uses it for years, and then they decommission that system and delete the bucket, is that name instantly freed up for me to grab?
This brings us to what's known as the cooldown catch. You cannot assume it's instantly available.
Okay.
While the name does eventually become available again, there is often a delay, this cooldown period, before another project can claim it.
And is that delay fixed? Like, is it 24 hours? A week?
It is not fixed or guaranteed, and this is a really important technical nuance. The duration is managed internally by the system. I mean, think about the complexity. GCS is a massively distributed system, globally replicated for performance. So when a bucket is deleted, that request has to propagate and be confirmed across multiple regions and data centers to ensure global consistency. The cooldown prevents, immediate reclamation conflicts. It makes sure there are no lingering references in different parts of the platform.
So if I delete a bucket and try to immediately recreate it, even in my own account, it'll probably fail.
It will likely fail with an error message forcing you to wait. And you have no visibility into how long that wait will be. It's a systemic safety measure.
That's a key detail, one that's definitely overlooked. So once I've successfully navigated this global name check, the bucket becomes my definition point. It's where I set all the configuration before I upload a single byte of data.
Correct. It defines the performance characteristics, what we call the storage class standard, nearline, coldline, archive, and of course the physical location, which we'll get into. And fundamentally, every bucket must be associated with a specific Google Cloud project. That provides the foundational link for both your cost allocation and, crucially, the security context within IAM.
Let's pivot to the strict art of bucket naming. Because of this global uniqueness and the need for DNS compatibility, the rules are, well, they're incredibly rigid. This isn't about preference, it's about adherence to technical standards.
Precisely. Adherence to these conventions is critical because GCS bucket names often map directly to URLs, like storage.googleassist.com and then your bucket name. So they have to follow web standards and DNS rules to be resolvable on the internet.
Let's run through the compliance check then. What are the allowed characters? What happens if I try to deviate even a little bit?
You're limited to a very specific set. Lowercase letters, numbers, dashes, underscores, and dots. That's it.
No uppercase letters.
None. If you try to use an uppercase letter or a special symbol like a $ or an asterisk, the API call will just fail instantly. It's a super common mistake for people migrating from systems that allow mixed case naming.
And what about placement? Does it matter where I put those characters?
It does. The name must begin and end with either a number or a letter. So while you can use an underscore or a dot in the middle, you can't start or end a name with them. For example, archive.data is perfectly valid, but .archive.data or archive.data is immediately invalid.
So no symbols as boundary markers.
Right.
And the length limits are surprisingly specific, especially that exception for names with dots.
Yeah, so the standard length is between 3 and 63 characters. 3 is your minimum. 63 is the limit from DNS standards for a single domain label.
But then there's this extended length.
Right. If your name is meant to look like a fully qualified domain name, for instance, data.us, east1.mycompany.com, it can be extended up to 222 characters. But, and this is the nested rule, each component between the dots still can't exceed that primary 63-character limit. It's designed to mimic DNS hierarchy.
And finally, the prohibited patterns. The things that might look okay, but Google will reject them every time for system integrity.
This is purely about avoiding conflict or confusion. You can't start a bucket name with Goog that's reserved for Google's internal use. You also can't contain the word Google itself, or, close misspellings like using a 0 for an O.
Prevents impersonation.
Right. And crucially, you can't format the name as an IP address, like 192.168.1.1. That would create obvious routing and resolution conflicts at the networking layer.
That level of specificity just underscores that GCS is this massive, globally interconnected system. You have to think globally and adhere to these strict web standards from day one, or your bucket won't even exist.
The compliance check is the architectural gatekeeper. It forces you to be organized and technically disciplined before you ever upload a single byte. And once you pass the naming rules, then you get to the location decision, which is where the real cost and performance trade-offs begin.
Okay, so the location of the bucket is probably the single biggest factor in determining cost, speed, and resilience. You frame this as the trade-off triangle, which is this constant balancing act between latency, availability, and cost.
That triangle is the lens every cloud architect has to look through for this decision. You can optimize for speed, which is low latency, or you can optimize for maximum survival, high availability. But trying to push both usually means you're going to sacrifice on the cost side.
So let's start with the most common one, optimizing for speed and cost. The regional location.
Regional storage is the most straightforward and, usually the most cost-effective option. Your data is stored in a single specific geographic place, like US East 1 in North America.
But it's still redundant within that region, right?
Oh, yes. The data is replicated across different availability zones within that region, so you have zone-level resilience.
Yep.
But it is geographically confined to that one spot on the map.
So what's the primary driver for choosing regional?
Low latency. It is absolutely ideal when your compute resources, your virtual machines, your AML training clusters, your serverless functions are sitting right next to the data in the same region.
It minimizes network travel time.
Exactly. It minimizes what we call data gravity, making it the fastest option for those localized workloads. If you have an intense regional processing job, say, financial analysis for New York traders, and all your compute is in a New York data center, then regional storage is the most efficient, low-cost choice.
But the trade-off is geographic resilience. If something catastrophic were to affect that entire region, the data availability is compromised compared to the other options.
Exactly right. You're essentially betting on the stability of that entire region. And that's why we move to the next tier up, which explicitly optimizes for high availability and recovery.
Which is dual region.
Dual region.
This sounds like a very specific solution, built for critical operations that need a fast recovery.
It is. It's a deliberate, highly engineered solution. In a dual region configuration, your data is explicitly replicated across two specific defined regions. They're often separated by hundreds of miles. The source material gives the example of NAM4, which pairs regions like Iowa and South Carolina.
So why not just use a multi-region bucket then? What makes dual region unique?
It's about targeting a different recovery metric. Dual region offers extremely high availability, but it introduces these highly efficient synchronization mechanisms, sometimes called turbo replication. Because the two regions are explicitly paired and known, Google can fine-tune the replication process between them for maximum performance.
And that fine-tuning leads directly to a critical metric you mentioned, the recovery point objective, or RPO. For listeners who might not be familiar, what exactly is RPO and what's the guarantee here?
RPO is the maximum amount of data, measured in time, that your application can afford to lose after a failure. So if your RPO is 15 minutes, it means you can lose up to 15 minutes of transactional data and still meet your business requirements.
And dual region offers a specific RPO.
It does. It offers an RPO of 15 minutes. This is a crucial contracted number for your disaster recovery planning. It guarantees that if one of the regions fails catastrophically, the replicated copy in the other region is, at maximum, only a quarter of an hour behind the primary.
That's huge.
It is. That level of near real-time sync is paramount for critical transactional systems, logging, or any operational data that just cannot tolerate significant data loss.
So the dual region choice is all about minimizing data loss at a very specific, very aggressive level. Now, if dual region is tuned for two specific points, Multi-region must be the top tier for sheer global survival.
Multi-region is the definitive choice for maximum resilience and global scale. Here, the data is spread across at least 2 regions, but within a much larger continent-sized geographic area like US, EU, or Asia.
So you're trading that ultra-low, single-digit latency you might get from being in one specific region.
For unparalleled geographic tolerance.
Right. And what's the availability assurance here? How does it achieve that?
So for standard class storage, multi-region offers the highest availability guarantee quoted, 99.99%. It's architected to withstand a catastrophic failure across multiple data centers or even a whole regional blackout. The mechanism is really elegant. GCS just automatically and intelligently serves the data from the closest available region within that defined macro area.
So if you're building a content delivery network or a massive web property serving users across an entire continent, this is pretty much mandatory.
It has to be. The slight increase in latency for retrieval is a totally acceptable trade-off for the confidence that your data will be available virtually 100% of the time, regardless of isolated regional disasters.
So to synthesize this trade-off, if I'm building a simple, high-throughput internal analytics system that runs overnight and needs to be cheap, I go regional.
Yep.
If I'm building a high-value transactional application that demands minimal data loss, I'm specifically choosing dual region for that 15-minute RPO guarantee.
And if you're launching the next massive global content platform aiming for maximum uptime for millions of users across the continent, you go multi-region for that 99.99% assurance. And the price reflects that increasing distribution and guarantee. You are literally paying for the system to worry about regional disasters so you don't have to.
We've established the container, the bucket, and all the strategic choices around it. Now let's drill down into the data itself, the object.
Right.
We mentioned GCS is a flat key-value universe. What does that actually mean for how we, the users, interact with our data compared to, say, a file on our desktop?
It means we have to completely discard that traditional file system model. An object is just the individual piece of data you upload, a picture, a large log file, a database backup. Because GCS is an object store, it treats every piece of data as a flat blob of bytes linked to a unique identifier, the key, inside the bucket.
So there's no tree structure.
None. Just a massive index of keys and the data they point to. It's a flat universe.
This leads us to the fundamental principle that really separates object storage from traditional file systems, the immutability principle. This sounds really important for application developers. Tell us what immutability means for an object in GCS.
Immutability means that once an object is successfully uploaded and written to the platform, its content is fixed. It is permanent. You cannot modify its content directly. You can't just open a 10-gigabyte file and change a single byte in the middle of it.
That is a huge paradigm shift. So if I upload a massive configuration file and then realize I need to update a single line of code inside it, what happens when I save the correction? Where does the old file go?
You are not saving or editing the original object at all. You are initiating an API call to upload a completely new version of that object under the exact same key name. The system performs a full replacement.
So what happens to the old one?
The old object is either deleted immediately and permanently, or if you've enabled object versioning on the bucket, it moves into a historical, non-current state.
Why does GCS enforce this so strictly? Why can't they just build in the capability to modify a few bytes like a traditional block storage system?
The enforcement is absolutely essential to maintain consistency in a highly distributed system. I mean, traditional block storage systems, they allow in-place modification, but they require these complex, resource-intensive locking mechanisms.
Like file locks or data transactions.
Exactly, to prevent 2 users or 2 processes from corrupting the file by trying to write to the same spot at the same time. Object storage avoids that entire complexity. By forcing immutability, GCS guarantees that any object at any given time is a whole, complete, and verifiable piece of data.
So there's no need for partial write locks or complex consistency checks.
None. Every write operation is just the creation of a new verified object. This dramatically simplifies the architecture and allows for that phenomenal scale and consistency we talked about.
So immutability is really the secret to its massive scale. And this connects directly to version control. If I replace the object with a new version, how is the old one tracked and identified?
Right, so if object versioning is enabled on the bucket, and I would highly recommend this for any data you might ever need to recover, GCS doesn't actually overwrite the previous version. Instead, every time you upload that modification, The object gets a unique identifier called the generation number.
So each replacement just bumps that number up by 1.
Exactly. It gives you an indisputable, immutable audit trail of changes over time.
Okay, now we get to the core myth that we absolutely have to debunk, the folder myth. If GCS is this flat key value store, why, when I look at the Cloud Console or I use the command line tools, do I see a perfect hierarchy? I see folders nested within subfolders.
Because that hierarchy is 100% a visual simulation. It's engineered purely for user convenience.
So it's not real.
It is not real. GCS is flat. It has no physical directories, no folders, no inode structures like you'd find in a Unix or Windows file system. The underlying storage system only sees two things: the bucket name and the object key within it.
So the magic is entirely hidden inside the object key itself.
That's it. The full name of the object, the key, is one continuous string. If that object key is, for example, Clients Financial Invoices 2024 Q1 Report.pdf, GCS just views that entire string as the object's name. It doesn't see clients as a container that's holding financial.
So how does the simulation work if the system doesn't even know what a folder is?
The GCS tools, so the Cloud Console, the client libraries, the APIs, they are all programmed to recognize the / character as a delimiter. So when you ask the system to list the contents of the client's directory, the API is actually performing what's called a list objects with prefix operation.
Ah, so it's just asking for all the keys that start with the string clients.
And then stopping at the next slash. The console then visually groups those results, making it and feel like you're traversing a directory tree.
So it's a convenience layer. It gives developers that file system familiarity, but the underlying mechanism is really just a fast index-based query.
It's a genius piece of architectural abstraction, really. It bridges the gap between how we think about file systems and the true object storage architecture. It lets developers organize data logically using path architecture. That's exercise B. But you have to remember that when you move a file, you aren't updating a path pointer.
You're actually deleting the old object.
Yeah, that's creating a brand new object with the same content under the new key. It's a copy-delete operation that's just disguised as a move.
Okay, so if the object key is the file name, then the metadata is the file's identity card. Let's talk about metadata, because this is the crucial information that describes the object without forcing your application to open a massive file and start reading bytes.
Right. Metadata provides essential descriptive properties. It's how the system, and crucially your downstream applications, understand how to categorize and handle the data. And we usually categorize this into two types: system metadata, which GCS controls, and custom metadata, which you control.
Let's start with the key pieces of system metadata that GCS assigns automatically when an object is created or changed.
We need to nail down the two main identifiers first. We already discussed generation, which is the unique ID for a specific object content version. But there's also meta-generation.
Meta-generation.
Which tracks changes made to the metadata itself.
Okay, that distinction is really important. Can you give us a concrete analogy to separate generation and meta-generation clearly?
Yeah, think of a book. The generation number changes every time you revise the content of the book. A new edition is published, maybe with updated chapters. That's a content change.
Got it.
The meta-generation number changes if you keep the book content exactly the same, but you change its properties. For example, updating the ISBN number, changing the format from paperback to hardback, or changing who has permission to read it. The underlying data, the words on the page, are unchanged, but its identity or properties have been updated.
That distinction is critical for auditing and lifecycle management. What other system data is essential, especially for web compatibility?
Content type is vital. This is the standard MIME type SO, image PEG, or application PDF. GCS uses this to tell browsers or other applications how to correctly interpret and render the file when it's accessed.
So if the content type is wrong, a browser might try to display an image as plain text.
Exactly. Or an application might completely misinterpret a configuration file. And then finally, we have the integrity checks. GCS automatically calculates and stores integrity hashes like CRC3D2C or MD5. These are used to guarantee that the file wasn't corrupted during transit.
From the moment you upload it to the moment it's written to disk.
Or when a user later downloads it. If the calculated hash on receipt doesn't match the stored hash, the data is invalid. It's an assurance of data fidelity.
Okay, now let's move to custom metadata. This is where organizations can really unlock powerful application performance by attaching their own domain-specific tags.
Custom metadata is just user-defined key-value pairs that are attached to the object. They follow a specific format, usually prefixed with XGOOG meta, like XGOOG meta project alpha. It's the application goldmine because it allows for fast, descriptive querying without ever touching the actual data content.
Let's apply this to that scenario from exercise C. A clinical research team is storing these massive DNA sequence files, which could be petabytes in size. If they use custom metadata correctly, they don't have to start expensive, time-consuming retrievals of those huge files just to find what they need.
Exactly.
So what are, say, 3 pieces of custom metadata that would provide the maximum utility here?
For a clinical research team, context is everything. They need tags that describe the file's origin and status without needing to process the core file content. So first, they might use experiment ID.
Right, that's essential.
It links the sequence file back to a specific research trial, a protocol version, or a batch number. This lets them query for all files related to one specific scientific study.
Okay, what's number 2?
Second would be sequence type. They have to differentiate whether the data is from a whole genome sequencing run, or maybe exome data, or RNA sequencing data. This tells the compute engine exactly which analysis pipeline to run on the file.
And a third?
I'd say patient status. This is medically critical. Defining the current status of the sample donor, control, active trial, historical, or pending review.
And the practical value there is immense. Their application can just execute a cheap, fast API call filtering millions of object keys by the metadata tag patient status equals active trial.
And they filter down to the exact sequences they need before they ever initiate expensive data retrieval and processing. That massive efficiency gain is the core benefit of object metadata.
It really is. The metadata acts as a high-speed index card system for your massive data library.
That's a great way to put it. You're trading a few extra bytes of metadata storage for a dramatic reduction in I/O operations and compute time.
So let's shift to essential maintenance and operations, specifically around cost and security management. First, let's quickly solidify access control.
So access control is just defining who can interact with the data. While you can use access control lists, or ACLs, directly on individual objects, that's kind of a legacy method, it is paramount to use identity and access management, or IAM.
Modern standard.
It's the modern preferred security standard. IAM provides centralized, auditable control via roles and permissions that you apply to users or service accounts at the project or bucket level.
And then we have the ultimate automated cost saver, the lifecycle policy. This feels mandatory for any organization dealing with aging data.
It really should be. A lifecycle policy is a bucket-level configuration for automating data management tasks. Its main goal is ensuring your data doesn't just sit in expensive storage tiers longer than necessary. It's how you manage costs at scale.
So how does it work? What triggers those automated actions?
It's based on rules that define 2 primary actions: either automatically deleting objects entirely or moving them to a cheaper storage class.
Yep.
And the conditions that trigger these can be pretty complex.
Like what?
You can trigger on age, for example, transition all objects to cold line storage if they're older than 90 days. You can trigger on versioning, like delete any object versions that are older than the 5th most recent version so you don't accumulate tons of historical copies, or even the specific date.
So if I have massive amounts of compliance data that has to be retained for exactly 7 years but is rarely accessed after the first year, I can set a rule. Move to nearline after 30 days, move to cold line after 365 days, and then permanently delete after 2,555 days.
Precisely. It's an autonomous mechanism. It ensures your older, less frequently accessed data moves down the cost ladder from high availability, high cost standard storage all the way down to low cost, low access archive storage without any manual intervention or scripting. This prevents your costs from just ballooning as your data lake grows.
And finally, 2 advanced object operations that showcase GCS's power beyond simple upload-download: storage class transition and object composition.
Right, so storage class transition is the operation we just discussed, but executed manually. The key insight here is that you change an object storage class, say, from standard to archive without needing to move the data. The underlying bytes stay put. GCS only updates the metadata and internal properties.
Which saves a tremendous amount of time and bandwidth.
It does. And object composition. This is a huge efficiency boost for things like log aggregation.
How does that work?
Object composition is when you concatenate or stitch together multiple existing objects into one single new object.
Okay.
And critically, this is all done on the server side within Google Cloud's infrastructure.
So if I have, say, 10,000 small 1 megabyte log files from IoT sensors.
And you need to combine them into one 10-gigabyte file for batch analysis, you completely eliminate the need to download all 10,000 files to your own machine, stitch them together locally, and then re-upload the massive result. It's a huge win.
That server-side efficiency is incredible. It dramatically reduces bandwidth costs, client processing time, and the complexity of your application code.
Yeah.
Wow, okay. We've covered the bucket's global uniqueness, the location trade-offs, the object's immutability, and the power of metadata. Let's try to connect all these discrete concepts using that real-world example of a global media streaming service, like the Netflix analogy from the source material.
Yeah, this is a great way to see how all these architectural choices stack up. A streaming service like that needs three things above all else. Maximum availability, low latency to the user, and, cost-effective archiving for content that's not watched very often.
So let's start with the big one, the location decision. Based on our trade-off triangle, what bucket location choice is absolutely mandatory for their core library of movies and TV shows?
They have to choose a multi-region bucket, something like the US or EU geographic area. Their primary goal is resilience against failure and guaranteeing a global reach.
Because if they used a single region, a regional outage could take the entire platform down for millions of users.
And that's unacceptable. By selecting multi-region, they get that 99.99% availability target. It ensures that if one data center or even an entire region becomes unavailable, the content just automatically streams from the nearest working location.
Okay, so that handles availability. Now, how do they manage the millions of movie files, resolution variants, audio tracks, without getting completely lost in a massive, flat database?
This is the simulated hierarchy at work. They would organize their objects using the /delimiter to create a simulated path. It mimics a conventional media server structure.
So the object key might look like genre year movie in Marion resolution.mp4.
Exactly. Or genre year movie in Marion resolution audio track.mp4. The file doesn't live in actual folders, but their content management system can easily query by prefix list everything under the Horror 2024 prefix, and it's effortless. It's practical, simulated organization layered on top of flat storage.
And finally, let's look at the true operational power of metadata in this scenario. How would a streaming service use custom metadata to make its application smarter and faster when a user logs in?
This is a massive efficiency gain. Imagine the service uses custom metadata like XGOOG Meta Content Rating. When a user logs in with a child profile, the application doesn't have to check some complex external SQL database to match the video ID to its rating. That introduces latency and database overhead.
That's good.
Instead, the application makes a single rapid API request to GCS, filtering the entire content list directly based on that metadata tag. It can just say, show me all object keys where XGOOG Meta Content Rating is not R-rated or NC-17.
That means instantaneous content filtering right at the source. The application doesn't even need to look at results that aren't compliant.
Precisely. When you are serving millions of requests per second, eliminating even single database lookups for simple attributes is a critical performance win. It really showcases why metadata isn't just documentation. It's a direct operational asset that dictates efficiency at scale.
Wow, that was a really comprehensive exploration of Google Cloud Storage. Let's try to summarize the core nuggets that we extracted from this deep dive.
I think the main takeaway is that GCS requires a different mindset. Buckets are strategic, they are global, they are unique management units that dictate your residency, your billing, and your access strategy. You have to treat their naming with the same importance as a domain registration.
And that location choice, regional, dual region, or multi-region, is that critical trade-off triangle. You're balancing cost against speed and resilience, with dual region providing that unique, critical 15-minute recovery point objective for minimum data loss.
Then the object itself is defined by the immutability principle. You never edit, you always replace with a new version. It's a key design choice that enables the system's massive, consistent scale. And that hierarchy you see is just a visual trick, the /delimiter used to simulate folders in a fundamentally flat key-value universe.
And we learned that object identity is defined by powerful metadata. Both the fixed system tags, like that crucial difference between generation and metageneration, and the custom tags that allow your applications to categorize and filter massive amounts of data efficiently, which dramatically reduces processing cost and latency.
Embracing those foundational concepts, the global, strategic nature of the bucket and the flat, immutable nature of the data is really the only way to correctly architect and optimize any system that depends on GCS at an enterprise scale.
So here is the final thought for you to mull over as you design your next system. We've spent time confirming that GCS relies on a simulated hierarchy for developer convenience. But if that folder structure isn't real, what are the broader security and governance implications?
That's a great question.
If a developer mistakenly assumes that the path is physical, like in a traditional file system, they might rely on tools that don't correctly handle prefix filtering, or maybe they fail to secure old objects when they're moved. If the path is just a tag, not a structure, how does that fundamentally change how you design your application logic when you're replicating data across projects, or auditing security permissions on what you perceive as a deeply nested directory?
You have to build your application logic to respect that flat reality, even if the console is showing you those nice, neat folders.
That object-centric worldview forces a shift in how you think about efficiency, security, and data lineage.
Think on that, and we'll catch you on the next deep dive.
See you next time.